This conference will now be recorded.
Good morning.
Good morning, ma'am.
Good
So
morning.
all of relaxed for a week, right? No answer for this?
Yes, ma'am.
Didn't relax?
Yes, ma'am.
Yes, ma'am.
Okay, come back. Let's start with the topic or wherever we had left last time. Suchi, can you tell me where did you stop? Where did we stop?
First order reaction.
What is that we were discussing?
Ma'am, graph.
Plot
Again,
log
After
versus
integration.
t to get straight line.
Arshita. Is Arshit or Arshita? I can see Harshit. Hello.
Yes, ma'am.
Nice to hear one male voice. Good. So you're coming for first time, dear Harshit?
Yes, ma'am. First class.
Fine. Just coordinate with your classmates and make note what has been covered till now. Fine.
Yes, ma'am. I'll do it.
Okay, thank you. We were actually discussing what?
Plot log versus t to get straight line.
Trupti, if you tell like that, Harshit will not understand anything. Which was the topic actually we started discussing?
First order reaction, ma'am.
Comes under which topic again?
Kinetic.
Anyone?
Drug
Asha?
stability.
Yeah, we were discussing about the kinetics of drug stability. See, when you just tell first order and the zero order, you can correlate this first order and zero order in with respect to other subjects also. So in our subject, we were discussing this concept to understand the stability issues of the drug or the kinetics of the drug, that is degradation of the drug. It is nothing but the rate process. It's also a type of chemical reaction which happens. So in related to that, we were discussing about the order of kinetics, okay, which helps us to understand how the rate of reaction is dependent on the initial concentration of the drug, which is undergoing degradation. If it is independent of the initial concentration of the drug, then you call it as a zero order kinetics. That's what we learned in the previous class. Zero order. If you just refresh quickly, zero order, that's what is independent of the initial concentration. And some of the important examples which can be related to our pharmaceutical subjects are this: degradation of the drug in solution, that is the suspension, photochemical reaction, and the color loss in multi-sulfur preparation. So these are some of the examples of the zero order kinetics. And the one thing to be remembered is it is independent of the initial concentration of the reacting substance. Nothing but in our case, the reacting substance is drug itself, because we are worried about drug stability. So drug stability can be disturbed because of many reasons. It may be due to the environmental factors like temperature, the presence of the oxygen, or the pH environment around it. Okay, so or the light, photosensitive drugs, those are called as. So like this, the degradation can happen by any process. And to understand that how fast that or like how much time it takes for the drug to undergo degradation, which is very important thing for us to come out with the stability, shelf life of the drug, which helps in deciding the storage conditions. So on this, whatever knowledge we are gaining out of this information, everything is applied with the intention of improving its shelf life, so that when it reaches the customer, that is the receiving end is the customer should able to get the required therapeutic action. Whoever has not muted, kindly mute yourself. So let's quickly go into the first order. I think I discussed about the first order also. The point to be remembered in the first order is what? It depends on this first power of the concentration of the single reactant. It depends on the first power. In the zero order kinetics, it is independent it is independent of the initial amount, but in the first order, it is dependent on the initial amount of the drug. Fine. So these are the equations which we have. I made you understand. I don't know how much you remember. The rate of change of the reactant, that is in our case drug, with respect to time can be represented by differential equation. Okay, this equation is further modified to understand how the change is happening with respect to two time intervals. Time interval is one is 0 in the beginning, that is the beginning when the reaction starts, another one is the t. So ultimately, whatever the initial step you may not understand also, but one thing, the last equation you should be able to remember, that is it is converted into a straight line equation. That's the advantage. The advantage of straight line equation is what? It helps us to easily calculate the rate fact, that is especially the k value. Slope, when you get the slope value, that slope value helps us to calculate the rate, at what rate, that is speed, at what velocity the reaction is happening. So that speed we want. So that helps us to understand how much time it is taking for the drug to undergo degradation process. So quickly, okay. So this is what I think even I explained other day. We can carry out the experiment at the different temperature and then understand what is the rate. As the temperature increases, the rate of degradation also increases. There is a direct relation with the temperature and the rate process. So for this line, if you take the slope, so you can easily calculate. When you calculate the slope for this each line, no, you can determine the k value. And what is the calculation? Slope is equal to 2.3 by k. I think that's the mistake. It is slope is equal to k by 2.3. I think I told you last class also there is a mistake. Kindly rectify that. I forgot to rectify that. So it is k by 2.3 supposed to be, not 2.3 by k. Slope is equal to k by 2.3. So you get the k value easily from this line. So using that k value, you can understand how the rate, how fast the degradation is happening with respect to every temperature. So when you look at this slide, you might feel a little complicated. It's the same equation, whatever it was derived here. Ultimately, that is the straight line equation. Initially, it was in the natural log form. When you integrate between the two intervals, it comes into a natural logarithm form, and then this thing converted into the common logarithm form. That's the reason 2.3 comes into picture here. The same equation can be modified as per our practical need. So when you just quickly recollect in the physical pharmaceutics laboratory in the B form, you would have done the first order kinetics, also the second order kinetics reaction. Okay, so there this kind of equation means the basic equation is slightly modified in the sense as per the practical need. So the equation can be modified as per the practical need. So I can modify with respect to the two time interval. Means I can convert the time interval instead of t0, I can write it as a t1 to t2. Means I want to know what is happening between these two time interval, not from beginning to end. I want to know in between what is happening. So I can even derive the equation. The furthest I can simplify the equation by integrating between the specific time interval t1, t2. So rest it's the same straight line equation. There is no change in the equation. The only thing is because it's been integrated between two time intervals, so I can further simplify to get the equation to calculate the k value. Means there are two approaches of calculating the k value. One is graphically you can calculate, where you plot the time versus the amount, that is amount of drug with respect to particular time to get a straight line. That's what previously we have learned. This line, whatever you're seeing here, no, this graphical representation helps us to calculate the k value graphically. Same thing I want to calculate using the equation also. I can calculate by modifying the equation such that you simplify the equation such to get the k value. So it is rearrangement of the equation. Whatever the equation is there, that's been rearranged such that you get the k value. So I can determine the application of these equations are what? It's been modified such that for the practical need, I need to have an equation which I can comfortably use it. Otherwise, the theoretical equation, whatever we derive, it may not help us many times. So either I can go graphically determining the k value. No, I want to calculate with the equation as approach, then I have to simplify the equation to the k such that I'll get the equation particularly for the k value. And again, it depends on whether I want to calculate from the initial time interval, that is the initial concentration, that is T naught at the T naught, to the Tn, that is end time interval, or I want to calculate between the any specific two time interval T1 to T2, then the concentration also become C1 to C2. So accordingly, the equation I can comfortably use. Either I can use this if at all I have a 2 time intervals with me and 2 datas are with me, then I can directly go into this equation. So advantage of this equation is what? I have the 2 values in my hand for the 2 different time intervals. Still I can calculate the k value, where I cannot plot the graph only with the 2 time intervals. For a graphical representation, at least minimum you should have 4 to 5 points. So no, I don't have that 4 to 5 points to plot the graph, but I have the values, information which would have collected for the 2 different time intervals. Still, I can able to calculate the k value even without drawing the graph. That's the advantage of this kind of rearrangement of the equation without even graphical representation. I can calculate the k value by slight rearrangement of the equation, and with minimum information or the minimum data, I can able to still calculate the k value. And that is what all this rearrangement is done for the practical purpose. You can stop me anyway, whatever possible, I can make you clarify your doubts. So that's about the first order kinetics. Again, just adding up to the same in continuation. I think you can remember this equation, A by A minus X. I'm sure this is what you would have remembered. That is ester hydrolysis, that which you have done in the physical pharmaceutics. This is the basic equation they have used. A is the initial amount, A minus X is the amount still remaining to be degraded. It is left out. So this is how the modification. Let's not waste time here much. Let's go to the next one. So zero order kinetics, we got an idea. We got an idea about the first order kinetics also. Example you need to remember is acid hydrolysis, that is aspirin hydrolysis for the first order reaction, and the zero order reaction examples are, that is photochemical degradation and suspension, the drug undergoing degradation in the suspension. All those are the examples for the zero order kinetics. So going ahead, fine, we got some idea. There's also something called as pseudo first order reaction, and where, see, order of reactions are what? A reactant can be 1, which is getting degraded, or reactants can be 2, that is A and B, which is degrading together to produce X and Y product. There are many possibilities. But in case of pseudo first order reactions, as the word says, it's a pseudo first order. That means it is behaving false first order. There are 2 reactants which is taking part in the reaction, but still it is understood based on the concept of first order reaction. So that's why it is called as pseudo first order, and the best example is acid hydrolysis of the ester is actually the pseudo first order reaction, because there are 2 molecules which are involved, but one molecule is in, that is one reactant is in excess than the other. So example, OH ion concentration is in excess compared to the ester, and it is determined by assay of the residual ester. So ester is in the lesser concentration and OH ion is in the excess concentration. So it is acid hydrolysis. Okay. Oh, I think it should be alkaline hydrolysis. I think it is a mistake in the slide. So it is a alkaline hydrolysis. I'll just rectify that later on. I'll just cross verify and let you know. So it's catalyzed by the hydroxyl ion. The degradation of the ester happens because of the hydroxyl ion which is present in the medium, that is water, and this hydroxyl ion is in excess. So that when the reaction happens between the ester and this hydroxyl ion, the ester reduces faster compared to the OH ion. Means the OH ion change, its amount is changing very less because it's always present in the excess. So the only change happening is the change in the ester content. So that's why, though there are 2 reactants are involved in the reaction, 2 reactants are which one? One is the ester and other one is the OH ions. So this OH ion is always in excess. Though there are 2 reactants, since one of the reactant is always in excess, its change is not obvious, but the change in the other reactant is very much faster. That is, the ester change in the amount is faster. That's why it is called as a pseudo first order. Okay, so instead of it is a second order, it is actually behaving like a first order. That's why it is called as pseudo first order reactions. So one example is alkaline hydrolysis of the ester. You make that point because we are mentioning OH ion, so it is alkaline hydrolysis. So that's about the pseudo first order. So this is how the graphical representation. I just want you guys to know how the data is represented graphically and what is the advantage of representing the data in the graph. The one advantage in the kinetic study, that is the stability study, the graph helps us to calculate the rate constant, that is the K value. And also it helps us to understand the visually how actually the line is shifting from one height to another level, means one level to another level. So you can carry out this degradation at the different pH environment also and understand the effect of the pH also. So there are many things, many kind of experimental procedure has to be added up depending on what is that you are planning to look for. Degradation in presence of the changing temperature or degradation in the fixed temperature at various pH environment, like this. So you have to plan the work to understand the effect of individual factor. So pseudo first law, I want you guys to just remember the kinetic stability aspect of the drug can be understood based on the first order, that is zero order, first order kinetics, and also sometimes the pseudo first order kinetics and even sometimes second order kinetics. So the complexity will go on as the order increases. So second order, this is the example, alkaline hydrolysis of the ethyl acetate is the second order reaction. When I say second order, remember there are two reactants. When I say first order, it is only one reactant, okay, which is involving. In the zero order, the reaction doesn't depend on the initial reactants. Okay, so that's why it's called as zero order kinetics. And when we say second order, there are two entities, that is the reactants which is involving in the degradation process. So best example for the second order reaction is alkaline hydrolysis of ethyl acetate, practically which can be done to understand the rate process. So as I said, more the order increases, as you increase the order of the reaction, the complexity of the equation also will be doubled. So as you can see right now, I'm very sure that is not, you can recollect anything or you can memorize anything when you look at the slide, but I just want to make you know that. So in the order of second order of reaction, there are two possibilities where A may be equal, it may not be equal to B, or A may be equal to B. What is this A and B? A is a reactant, first reactant, and B is the second reactant. So there is a chance that one of the reactant may be happening in a faster rate compared to the another reactant. So not equal. Equally, the number of moles of A and number of moles of B are not equal to each other. Then the totally the kinetic equation will be different for that. If the A is equal to B, where the equal amount is taking part in the reaction, then the equation is something else. So like this, just remember, as the order of the reaction increases, the complexity of the equation also increases. Okay, so in the pharmaceutical industry, there are all possibility of the degradation process or possibility of the degradation orders. So it cannot be always zero order or it cannot be always the first order. Even there are reactions, degradation which happens even the second order reaction are much more complex than that. But ultimately, we need to come out with an analytical procedure which helps us to determine this kind of degradation happening and use that information for our purpose. So quickly, I just want to know, that's about very brief actually, very brief. You don't scratch your head also. You need to just remember the order of reaction. At least you should remember the straight line equation for the zero order reaction, straight line equation for the first order reaction, and to an extent straight line, that is equation for the second order also you can try to memorize. In all the cases, ultimately we calculate one important value, and that value is called as K value. And what is that K value? It is nothing but the rate constant. What is its use? The rate constant helps us to understand the speed of the degradation. Why you want to understand the speed of the degradation? So that helps us to determine the shelf life of the drug. Okay, how long the drug will be stable at that particular environment, at particular temperature. Fine. With that information, what is that we are going to do? That based on that information, we are going to decide about the storage condition, or we are coming out with the some altered formulation procedure which will not disturb the stability of the drug, which would have been not disturbed during the processing. So like this, many kind of decisions can be taken very valuable decisions can be taken based on this stability study. And that helps us to come out with a stable product even after reaching the customer. Not just till it reaches customer, even when till the customer uses, till its shelf life, the stability of the drug should be retained. So all this can be done with this that is kinetic aspects. Okay, so quickly let's enter into the one of the important factor which actually affects the degradation process is the temperature. Is the most important, and followed by that it can be the humidity also, it can be the light also, or any other environmental factor. Fine, we got to know little idea about the order, but you should also understand, for example, I have a drug molecule A with me. How long, how long it will be stable? To get an idea, I cannot waste my time for 1 year, 2 year, and 3. Maybe it might be taking 3 years, it might be taking 4 years to get degraded. We are not sure about that. So I cannot just wait for the drug to get degraded and get the information later. So I need to come out with the experimental procedure such that I can accelerate the condition. I can fasten the condition, the degradation condition, and I can determine the required value. And that's when the accelerated stability study comes into picture. So in order to get the information at the earliest, okay, so that we can minimize the time taken to understand the detailed procedure, to minimize the wastage of the time, okay, even the money which is getting wasted on that duration to study. I can carry out a study called as a accelerated stability studies. So according to the rule of thumb, I think you should be knowing this, there is a direct relation between the temperature and the rate, that is degradation rate, or any chemical process. For example, degradation is also a chemical process, definitely. So double the reaction expected to double. That's what the thumb rule says. So according to this thumb rule, what we have to remember is the double for means the reaction said to be doubling for every rise in, that is every 10-degree rise in temperature. So every time when I increase the temperature, the whatever the reaction rate was there, that will double, means that will fasten the process. So now that becomes easy for us to predict the stability of the product at ordinary shelf life. That is means I accelerate the temperature, then I extrapolate the data such that at room temperature, how long the product will be stable. At the room temperature, the drug might degrade at a very slower rate. That's the reason it might take 2 years, 3 years, or 4 years, or more than, or it may be even stable for 10 years. But I cannot wait for 10 years. So what I do is I accelerate the condition, I determine the rate, then I extrapolate back to the room temperature and calculate what might be the stability of the drug at the room temperature, how long it can be, it will be stable. So that's the advantage of the accelerated stability study. So when we talk about accelerated stability study, of course, it comes to our mind, first thing is the Arrhenius equation. So we are not deriving any of this equation. You have to just memorize this equation. And here also I'm stressing one point. Any of the kinetic equation is a straight line equation. Here also it is a straight line equation. Straight line equation is which one? Y is equal to mx plus c. What's the advantage of straight line equation? We get a linear line when the graph is plotted, and the slope value will give us the k value. That's the advantage of the straight line equation. And this is the basic equation of the Arrhenius equation, which is represents the reaction rate with respect to temperature. K is the reaction rate here, specific rate of degradation. R is the gas constant. Okay, we represented by 1.9. It is a constant value. The value should be memorized. And T is the absolute temperature. Okay, A is the frequency factor. That is a collision between the two reactants which is taking part in the reaction. And EA is the heat of activation. So, okay, it's more of chemistry. So EA is the heat of activation. So Arrhenius has come out with is one of the equation which helps us to understand or correlation. It gives the correlation between the rate of reaction with respect to temperature. Okay, and how it is advantageous for us, it helps us to understand the speed of degradation. So this basic equation was modified to a straight line equation. This is what I was telling you, straight line equation. And I expect you to add both the equation, the K. When they ask you about Arrhenius equation, you should know about this first equation, which was for the integrated. And then we got straight line equation was derived. Fine. So try to memorize all this. Whenever you write any equation, make sure that the alphabetical representation should be mentioned clearly what it stands for. So with the basic equation of the Arrhenius equation, so what is Arrhenius equation you understood now? It helps us, this is an equation which gives the relation between the rate, that is a degradation rate with respect to temperature. Now, using that equation, let's understand how that can be applicable for our purpose, how it can be used for our purpose. So if you look at this graph, there are two things you can see. There are K value in the y-axis, correct? And there is a time factor in the x-axis. Means I have a sample with me. I want to understand this degradation process. So what I do is, don't worry at this point in what mechanism the degradation is happening. Let us not worry. Means it is temperature dependent degradation happening. That's only I can tell you right now. So change in the temperature means it is temperature sensitive. Means, so what I can do is I can carry out the procedure at different temperature. Okay, like 40 degree, 50 degree, 60 degree. I cannot carry out at 30 degree, 20 degree. So carefully notice here dotted line, whatever you can see here. This is dotted line. That dotted line is actually the line which we are extending later on after plotting the graph. So what we have to do is, initially you carry out the stability study at the different temperature. So what temperature? Much more than the room temperature we have to, like 40 degree, 50 degree, 60 degree, 70 and 80. So you can imagine there are 1, 2, 3, 4, 5, 6 graphs we have to draw, because 6 graph is what? It's the ordinary graph which is plotted between the time versus the concentration of the drug at particular time. So we have a 6 graphs, and from each graph you calculate the K value, that is K value for the 40 degree, K value for 50 degree, 60, 70, 80. So how many K values we have? 5 K values with us. Once the K value we have got it, this graph comes into picture. This graph is not directly from the first experiment. We have to carry out the experiment at different temperature, determine the K value, then you plot this graph, which is the Arrhenius graph, where you're plotting the K value in the y-axis and then the x-axis is 1 by t. And this is nothing but the straight line equation which we have understood previously. This one. So K value here, if you look at carefully, this is equal to y is equal to mx plus I told you. This is mx, x is 1 by t. Okay. This is y. This is the y, mx. Okay. I'm very finding difficult to write. Mx plus this is the c. So y is equal to mx plus c. So which graph I can plot now? In the y-axis it is the log k, and is the x-axis is the 1 by t. Fine. And what is the slope? From the slope we are going to get the delta EA by 2.303 R. That is R. Means you get that entire value for that factors. Okay. So this is the advantage of the graph. Once you plot the graph, so fine. So you can determine the EA value from the slope. So plot K versus log K versus 1 by T value. That's what. And the K value is determined at element. That's what I was telling you, the procedure, how you have to do. Carry out the stability study at the different temperature. Note down the K value, plot the K value in the y-axis and the 1 by T value in the x-axis. And the log K versus whatever the graph you plot, you get the slope which is equal to delta E by 2.303 R. You know the R value, I told you it's a constant value, 1.987. You substitute that R value in that equation, and slope value will get in the left hand side of this equal. So slope value will have, you just do the cross calculation, you are going to get the delta E value. So there is an advantage of calculating the delta E value. Higher the value of the EA, more the stability in the presence of temperature. So you get additional information also, means higher the EA value, you can conclude that. So lesser the EA value means they are not stable as the temperature increases. So okay, fine. I have this information. So what is the use for me? What I do next? So I want to know my stability of my drug at the room temperature. That's what my intention, right? I don't store my drug at 50 degree or 60 degree, but I have carried out the experiment at 60, 70, 80 just to accelerate the condition. So what I do it, this dotted line, I extrapolate the line backwards such that it is 30 degree condition it gives us and 20 degree conditions it gives. So I can extrapolate to the y-axis, this one, this way. This is the temperature I got, okay, 30, 20 degree, fine. Now I do is I extrapolate to the x-axis. So what information I get here? I'll get an idea about the rate constant K. What may be the speed of reaction at the 30 degree? And what may be the speed of reaction at the 20 degree centigrade? So this helps us to understand the condition of your drug or the stability of your drug at that particular temperature. Later on, this information further they use it to understand like how long your the drug will be stable. As I said, months or years. Any doubt running in your mind, you can stop and ask me. Fine. That's about the Arrhenius stability study. The advantage is this stability study helps us to carry out the stability of the understand the stability of the drug by carrying out the experiment at elevated temperature. Why you want to elevate the temperature? Because you want to fasten the reaction. So why you want to fasten the reaction? Because the drug degradation at the room temperature will be very, very slow, and it might take many months or years together, and we cannot wait for that to happen for months or years together to understand the number of days the drug is stable. So what we do is we aggravate the that is accelerate the reaction by increasing the temperature with the confidence of what the drug is getting degraded by increasing the temperature. So once we carry out the experiment at the elevated temperature, that is accelerated temperature, we do the extrapolation of the data towards the room temperature to understand the speed of degradation at room temperature. Fine. But as I said, again the equation can be slightly modified to our need. Practically, I may not have a sufficient data. To get this straight line graph, I should at least have 4 to 5 points. That's what I was telling you. Okay. So if at all we don't have that 4 to 5 point data, means I may have only 60 degree data, I may have only 50 degree data, but still I can calculate the EA value. Means I can modify the equation such that even with the minimum value, I told you before also in case of second order, that is first order reaction, equations are modified such that it will not disturb, rearrange such that it will not disturb the basic equation. So whatever equation you are seeing here, this one, it is the equation which is being slightly modified with respect to the basic equation, this one. Okay. So when you rearrange it back, it comes back to the same equation. So two different temperature, I have the value with me. Still, I can calculate the EA value. So with the two minimum data, I can still able to calculate the delta E value. And that's the advantage of deriving an equation, Arrhenius equation with respect to two temperature values. Okay, that's about Arrhenius. Anything you would like to ask me? Fine. So quickly, let's understand. Can I use the accelerated stability study for everything? For whichever drug I want to know its stability, can I go with the accelerated stability study? When the word comes accelerated stability study, remember it is always with respect to increase in temperature. Arrhenius equation mainly talks about the effect of increasing temperature on the reaction rate. So it's not possible to apply for all the degradation process. There are certain things it has to, the criteria has to be, it should meet certain criteria. So some examples I just highlight here. The solvolytic process, some of the process which can be done. The first one is the solvolytic process. Okay. So generally this solvolytic process is one of the degradation procedure which get affected by increasing the temperature. So it's EA value. So most important for us to helps us to decide whether I can go with the Arrhenius accelerated stability study is the delta EA value. If the process is happening, if the delta A value is between 10 to 30 kilocalories per mole, any degradation which has an EA value, which is dependent on the temperature, if its EA value is between the range of 10 to 30 kilocalories per mole, that is the unit of the EA value, then only we can expect that accelerated stability studies can be carried out. Means there is a change happening with respect to increase in the temperature. If the change doesn't happen with increase in temperature, which it cannot be observed from our side, then we cannot go with the accelerated stability study based on RNA's concept. So there should be change which should happen in the presence or with the increase in the temperature, and when that change happens, that EA value should be within the range of 10 to 30 kilocalories. So okay, so another example is solvolytic process. So another one is photolysis process. So look at this EA value, it is 2 to 3 kilocalories per mole. Okay, fine. Compared to first one, 10 to 30 kilocalories more EA value, this is quite lesser than that. But still, it can be used. It has a little advantage of increase in temperature. Means what is this means is, I increase the temperature like 60, 70, 80, 90. This increase, even 90, 110, you keep on increase to a certain level. I cannot keep on increasing to 200, 300. You know what is the reason for that? The reactant will get destroyed at that higher temperature. We don't find any advantage of increasing the temperature. It may not, obvious change may not be visible because of the delta. Its reaction is, the delta E value is in the range of 2 to 3 kilocalories per mole. So you don't find much advantage with this kind of reaction rate, which is in the range of 2 to 3 kilocalories. The last one is the pyrolysis, which is not possible to consider at all, whose delta value is 50 to 70 kilocalories. To get this value 50 to 70 kilocalories, it's quite high temperature has to be used. Till then you don't find any change in the delta E value. You don't see any effect of temperature on the reaction. So you cannot expect this kind of reaction to product undergoing with this delta E value. You cannot determine by the accelerated stability study. It's because it is a practical significance. When you talk about the practical aspect, you don't generally go with that higher temperature. We don't store our products such a higher temperature. For example, generally room temperature depends on the zone. For example, east, west, north, south zones, where the temperature may be maximum like 47 degree, 45 degree. So like this. One second. Oh, fine. So I was just talking about what kind of reaction. Means any reaction which is dependent on temperature can only be understood based on the RNA's concept. Again, in that, what kind of effect the temperature has on the reaction rate. Okay, that can be understood with the help of the value called as delta EA value. So any reaction happening at the presence of particular temperature, there will be a fixed delta EA value. Okay, for that particular temperature. So this delta EA value is the deciding factor for us to know whether I can really carry out the stability study at accelerated conditions or not. So the ideal range of EA value to be accepted to carry out the stability study by accelerated temperature is 10 to 30 kilocalories per mole. If the reaction is happening with the delta E value between 10 to 30 kilocalories per mole, then only we can expect change happening with the increase in the temperature like 60, 70, 80, 90, 100 when I carry out. So the obvious change will be happening, and I can easily calculate the different K values and plot the RNA's plot. If not, the other two cases where the 2 to 3 kilocalories doesn't have any advantage, because though change is happening, it is not a very obvious change which is happening, helps us to determine the K value. This obvious change will not happen. And the next one is 50 to 70 kilocalories, which happens at very quite higher temperature, and no point for us to carry out the stability study because it is stable that to particular, it's not the temperature, it's much above the room temperature condition. And generally we don't want that to, we cannot consider at all. Its stability is not dependent on temperature. It might be getting degraded because of some other reason, but not because of the temperature. So, any doubt? So anyway, I'll discuss further later on. I need to wind up the class now. Do you have syllabus copy with you? Syllabus with you, which I shared that long back.
Yes, ma'am.
Yes, ma'am.
Please go through, all of you go through the validation chapter. Just go through validation topic. I'll come back with the topics for the seminar. You can just go through the topics. I'm not asking you to go in detail, just superficially go through the topic, and I'll make the seminar topics. When I share the topics, you should take your interest among the topics which is there in the validation chapter. Okay, so we'll meet tomorrow.
Okay, ma'am.
Okay, thank you. Bye.
Thank you, ma'am.
Thank you, Suchi. Thank you, Asha.
Thank you, ma'am.
Thank you, ma'am.
Harshit,
Thank you, ma'am.
Yes, ma'am.
when did you join actually?
Regarding what, ma'am?
This when did you actually join officially? I mean, when actually you started attending the classes?
Today only, ma'am.
Today only mine, but long back I received message that there is a person who is joined, but last week only.
That like right before the holidays were announced.
Before holiday, dear. Why I'm telling this? Because take care of your attendance also. 80% is mandatory. Okay.
No, ma'am. Like the holidays, the
No
from
holidays, dear.
25th. I
Before that
joined on the
only I
25th.
received message that that one person called. I thought Harshita it is. I read it as Harshita. So anyway, I'm just stressing upon the attendance component. Take care of
Yes,
attendance.
ma'am.
Okay. Okay, dear. That's it. Thank you. Bye.
Thank you, ma'am.